Hi everybody and welcome back. So our next talk is on microservice patterns with Akka and Kafka. Oh, hold on. I may have possibly just dropped off. Can you guys hear me?
Yes, we can now.
Oh, thank you. That's excellent. Right, so I'll introduce you again, Aleksandar. Our next talk is going to be on microservice patterns with Akka and Kafka by Aleksandar, who is a software engineer from Serbia. He works with Java a lot, but he really loves Scala, as do we all. But he started his career as a data scientist and switched to software engineering. So I think that this talk is going to be pretty interesting insights in how Akka and Kafka can be used perhaps for those purposes as well. Now, he also is going to speak and takes part in a data science meetup in Serbia, which has virtual conferences, and I'm going to share that with you in the chat. The next meetup is on June the 23rd, and it looks to have some pretty interesting talks. And you can take a look at it there. Okay, so without further ado, I will hand over to Aleksandar.
Thank you, Zainab. Before me, it was Chris. A really nice talk, but now it's my turn. And I will talk about some common patterns that you may encounter while working on streaming or event-based architectures. So here's a talk flow. You can see that we are going to talk a little bit about Kafka and Akka. And after that, I will talk about Akka Streams and about application of Akka Streams and integration with Kafka, and finally show how it looks in a code with a few examples. And that will be available on a GitHub tomorrow, I think. Before I start, I think I should introduce myself. So my name is Aleksandar. I am software engineer from Serbia, Novi Sad. I work for a company called SmartCat, and we are doing big data, microservices, and machine learning. And here is some of my social network profiles, so you can contact me whenever you want. What is Apache Kafka? Is basically our first question, and I will try to give a really fast explanation and introduction of Apache Kafka. Apache Kafka is a really hot project right now, and I assume that a lot of developers are already familiar with at least basics of Kafka, so what it is and what are some common use cases of Kafka. Apache Kafka is a distributed streaming platform, and this is a description from official website. But in a nutshell, Kafka is a message broker, which is distributed by design, and it's pretty scalable and resilient, and it enables publish-subscribe messaging model. Kafka is often basically in a cluster, where each node in a cluster is called a broker. So broker is basically just a server that runs Kafka node. Kafka cluster stores streams of records into something that is called topic. And you can think of Kafka topic as a database table, but without all the constraints. And each topic is identified by its name. And you are basically the number of topics is unlimited for the Kafka cluster, so you can have as many as you want. So now, when we are familiar with the basic concept of Kafka, let's review some typical Kafka workflow. Here, on the left side, we have a Kafka producer, which is used to produce a record to topic. And this is Kafka topic, and it's usually divided into one or more partitions, and each partition is append-only log. That means when a producer produces a record to a partition, it will be put at the end of partition, and the partitions are immutable, and once message is written to it, it can be deleted or modified. So topic partitions are distributed between multiple brokers, and every topic have a replication factor. And in practice, replication factor is most usually 3, which means that every Kafka topic will have 3 copies on multiple brokers. Each partition is ordered, but order of messages is guaranteed only within specific partition, not across topic and across multiple partitions. And each message inside partition gets own incremental ID called offset, and which is a pretty important concept in Kafka, and soon you will see why. So if message is newer, it will have a higher offset. Messages in Kafka are kept for a limited amount of time. Default period is 7 days, and this is called retention period, but it's configurable, so you can keep your data as long as you want, even forever. And even when some records are removed when retention period expired, offset of message will keep incrementing. It won't reset. Also, a producer can assign a key to every record that it sent to a topic, and the key can be anything like string, number, or some even custom type. And if record key is null, data will be distributed around partitions in a round-robin fashion. But since Kafka 2.4 version, there is something called the sticky partitioner, and that uses some better algorithm than round-robin to distribute message across partitions. On the other side, if record they have a key, then all messages with that key will end up into same partition. Of course, this will not be true if after some time we change the number of partitions, because the hashing algorithm depends on the partition number. Here is one example why you should use Kafka message keys. So let's say that we are collecting temperature data for some location, and we want that data to be ordered, and we should then we should select some property like location ID or location name to be our message key, and in that way all data related to our specific location will be stored in order inside one partition. Producer will automatically do the key hashing for us, but you have an option to provide a custom partitioner if you need. Now, get data into the Kafka, we need to read it and process it in some way and apply some business logic on the messages. And for that, we are going to use Kafka consumers. And Kafka consumers are usually grouped in something that is called consumer group. And each consumer within consumer group reads from exclusive partitions. And if you have more consumers in a consumer group than partition, then some consumers will be inactive. Or if you have more partitions than consumers, then some of consumers will consume multiple partitions. So consumers read data from partitions sequentially, and after record is read, offset of that message should be committed. And if consumer dies, it will know from which offset it should continue to read, because previously we committed offsets of processed message. By default, offsets are stored in a special Kafka topic called consumer offsets, but besides that, you can use external offset storage also. So when consumer is restarted, it will just look at offset storage, pick last committed offset, and start to read everything after that. You can also enable auto commit offset option, but it's not safe, since you can lose data and don't have explicit control of committing. So best practice is to manually commit your offset, since in that way you have a full control of when you want to commit offset, and usually it will be after you process your message or batch of messages. Now let's just review what we learned about Kafka. So Kafka, as we already said, is just a message broker. It has 4 core APIs: producer, consumer, Kafka Streams, and Kafka Connect. These last 2 are just out of scope of this presentation, but I hope that this was enough for you to understand what Kafka is and what problems it solves. So some common use cases of Kafka are inter-service communication in event-based or microservice architecture, real-time data pipelines, and stream processing. Now we finished with Kafka section, and we're going to talk a little bit about Akka. So Akka is a toolkit for building concurrent and distributed and message-driven applications for Java and Scala, of course. Akka is just an implementation of actor model for JVM, and the idea of actors is really old. It's nearly 5 decades old, and it's popularized by Erlang programming language, which is used to build highly concurrent and distributed telecommunication systems. What Akka can do for us, basically Akka provides a unified programming model for simple concurrent programming, because when you are programming with Akka actors, there is no need for a locking or synchronization mechanism. Distributed computing can be pretty simple with Akka, so there is no big difference between single node or multi-node Akka applications. You just need to modify configuration files a little bit. And Akka also have a great fault tolerance mechanism, since actors should be organized in tree-like structures where actors higher in the hierarchy can supervise their child. I said that Akka is message-driven, and that means that communication between actors is based on asynchronous message passing. I also said that there is no need for locking or synchronization mechanism, because actor state can be modified only by sending message to actor, and it only process one message at a time. So review of actor model. So basically, when you're programming with Akka, every component basically would be an actor, and since actors talk by sending messages to each other, every actor has an address. And what actor really can do, basically just these 4 things. When actor receive a message, it can create new child actor, it can send message to some other actor, and it can mutate local state, or it can just change the behavior for handling the next message. And I here provided a simple implementation of actor. So when we define actors, first we need to define our protocol. And protocol is just a set of messages that our actor is able to receive. Here we have our response protocol, since some other actors can ask us for our state. And here's just a case class that represent our actor state. I forgot to say that this is device actor. Basically, it was just blueprint of some IoT device, and basically we just want to store our air quality and temperature, and we just want to be able to send our state to our requesters. So first step in defining actor is basically providing this apply method, and just to initialize our actor state. And in process message method, we defined our business logic. So we need to provide the partial function, basically, that receive actor context and message that is received, and it will just return another actor behavior. So we can receive update air quality message, update temperature message, and those 2 are handled in the same way. So basically, when we just receive update temperature message, we'll just create our new state with update temperature, as set our next behavior to be the same as this one, but with a new state. And when we get state request, alongside the state request, we will get our requester, and we will use this requester reference to just send them our current state, which will be wrapped in this state response. And here is just a starting point of our application. We will create our device actor. We can send a few messages to it, and then we will ask for state, and the actor will just return us future of response, because I already said that everything is asynchronous in Akka. And after that, we'll just attach our onComplete callback function and just print our response. So basically, it's just a dummy actor, but I think it's enough to give you, just a look and feel of how Akka actors are implemented. And just a note for you, this is a new actor typed API, which is slightly different than classic API. And this is recommended way from now. If you're starting your new Akka-based applications, basically it's better to use Akka typed than Akka classic. Now, a little introduction to Akka Streams. Basically, Akka Stream is just DSL that provide us some high-level operators to deal with the stream processing. It is built on top of Akka actors, and every one of us know what is stream. Basically, it's just a sequence of elements that potentially can be infinite. So core components of Akka Streams are source, flow, and sink. And Akka source is just a starting point of our stream, and it will have just an output. Flow is basically a little slightly more complex component, and it will just transform. It will be used just to transform our message, and it can have input and output. And Akka sync will be just a termination point, the final destination of our stream. So using these three concepts, you are able to construct very complex stream processing topologies. So here is just a simple example of a stream processing topology. Let's say that we have some list of tweets, and you can create Akka source from list, from Scala future, from Kafka topic, basically whenever you data source you can imagine. So just for the purpose of learning, I will use just a list of strings. Then we'll need to define our flows. Basically, we just want to extract the words from hashtag. So we will, in this flow, just return a hash. We will convert every tweet to lowercase, and we will just take one that is longer than 3 characters. And our sync will be just a dummy sync that will print every element it receives. So we have some our components of stream, but we need to wire them together. And for that, we can use via method that is used to connect source and flow. And the to method is a way to connect source with a sync. And what we have here is a runnable graph, and it is just a blueprint of our stream processing topology. And in order to run our stream, we need to just invoke method run. If you doesn't just invoke this run method, it will do nothing. And this run method, in order to work, you need to have implicit actor materializer. But since Akka 2.6, there is just enough to have an implicit actor system in a scope, and actor materializer will be provided out of box for you. But if you're using Akka less than 2.6, then you will need the implicit actor materializer also here. So this is just another way how you can represent the sync. Basically, you don't need to specify components separately and then wire them. You just use this builder-like pattern to build your pipeline. This is even shorter, basically. Example. And this is where I should explain why you should use Akka Streams. Basically, I already said it have a great declarative API. It has great integrations with other systems. So you can use Akka, you can use Kafka, JDBC, Cassandra, MongoDB as sources or syncs to your system. And the stream supervision is also great. actor API. And what is most important is that every Akka Stream topology is back pressure aware by design. So as a developer, you don't need to write any back pressure handling code explicitly. Akka doing that for you. So what back pressure is? Back pressure basically is a problem that that we can encounter here is when we have a fast producer, slow consumer, and after some time, our consumer will be overwhelmed by the messages that comes from fast producer. So when your pipeline is back pressure aware, that means that your consumer will dictate the pace. So when your consumer is ready to process messages, it will just notify producer about that, and producer will send message or batch of messages of to this slow consumer, and this means that your pipeline are back pressure aware. So we covered a lot for now, like Kafka, Akka, and Akka Streams. And now I want to show you a few examples. I coded 3 or 4 examples, and just want to review them together. First one will be how can you parallelize your stream processing. Another one will be how you can integrate actors and stream together. Basically, this one is the most interesting to me. And I will show you how you can handle basically WebSocket connection with Akka Streams. And basically, we'll just code a simple pipeline that will read events from WebSocket and publish that to a Kafka topic. And finally, we will implement some simple rate limiter with Akka Streams. So the first example is how you can parallelize your pipelines. There is only 2 methods for that, map pacing and map pacing unordered. Signature of this method, of both these methods, is basically the same. The first argument is level of parallelism, and another one is a function that will be applied to every stream element. So this how this works. When some elements came to this stage, 4 futures will be spawned in parallel, and when all futures are completed, then elements will be passed downstream in the same order that they come. And what is only difference between these 2 methods is that the second one will not preserve stream order, but this method is much more performant. So this will also spawn the 4 futures in parallel, but when the first future is completed, it will pass that element downstream. So if you don't care about order of your stream, you should use map pacing unordered function. So this is how it is easy to implement parallel stream processing with Akka. And this could be really helpful with your Kafka pipelines, because if you just use Kafka consumer, it can be really hard to parallelize your batch processing with Kafka, with plain Apache Kafka client. Another example will be much more complex. We're going to have order topic where our orders will come from some external system, and every order will have a list of items, but the item price is dynamic, and on the other side we will have topic will just receive item updates, and we'll have item state actor that will hold all items state in memory, and this order actor will be responsible for processing orders. Basically, when order actor receive order, it will ask this item state actor for current state of the items. It will do some validation, and the order can be approved or rejected, and it will be pushed back to some queue, Akka Stream queue, and this Akka Stream queue will just filter these 2 into different Kafka topics, order or rejected, and later you can just add some WebSocket service that will basically read these 2 Kafka topics, and via WebSocket just send a response about order to client, to frontend. So let's see how it looks in a code. So we will have item state actor. It will just have hash map of items. It will basically directly receive the messages from Kafka and store that in memory. So here is our protocol. I simplified here a little bit to have enough space to, but in the GitHub you can see the full source code. So let's just see our business logic in process update method. So basically, we can receive item update from Kafka, or we can use get items from order actor. So when we receive message from the Kafka, we will just process it in some way, and you see that we're just sending back pressure signal back to our Kafka to say that we are ready to receive some more events. And when we get items request, we are going to get list of items IDs, and we'll get here order actor reference. So basically, we'll just extract for our state every item current state. We'll wrap that to a item response and set back to order actor, who is basically the requester, and behavior will remain the same. Now, order actor is a little bit more complicated than item state actor, and you will see why. I'll just skip, basically first, I will skip this slide, but come back later to this. So order actor, this is the business logic of our order actor. Order event is received from Kafka directly, and when we receive the order from Kafka, we will extract item IDs from the event, and we're going to ask item state actor about items. And when we get the response, we are going to wrap it in our adapted response, because we need to make this message compliant with our protocol, and our protocol is we cannot directly receive message from other actor. We need just to adapt it to our protocol. So we'll when we got a response from item state actor, we will pass this message to ourselves, basically order and updated items, and then here we are going to do some validation. And if order is approved, we will just wrap order in order approved case class and push that to a queue. And if order basically is rejected, is not valid, we will wrap that in order rejected case class and push that back to a queue, and behavior will stay the same. And this queue is pretty interesting. So basically, this is a queue that dynamically can be filled. Basically, we are creating Akka source, and later dynamically from our code, we are able to push data to it. So this process order queue will receive orders, and these two orders can be approved or rejected, and we will just wrap them to instances of either. If order is approved, we will wrap that to right, and if it's not, we will approve that to left. And we have these two sinks. This is just dummy sinks. Those sinks are basically these two queues. I just made them dummy to print everything that it received, but it can pretty easily be replaced with Kafka topic. And this is it. We are just going to have some supervisor actor that will be responsible for creating those two actors and creating, just to create these two actors and to bootstrap our application. I just mocked this source. I didn't use Kafka directly, but it can easily be replaced. I have some examples on GitHub, and I will share that with you so you can play with this example and even make them better. And this is just the simple actor method that is used to create actor as a sink. So basically, you just need to provide actor reference, and this is just some messages. And this basically Akka message is most important to notify our sender that we are ready to receive some more. Another example is how to implement WebSocket to Kafka Pipeline. So imagine that you have some external API that pushes some events via WebSocket, and we need, just to capture that event, process it in some way, extract some informations, and put that information to Kafka topic. So this is the whole pipeline, believe it or not. I will just walk you quickly through the implementation. So you can use Akka Http WebSocket client to connect to your WebSocket connection. So it requires WebSocket URL and WebSocket flow. And WebSocket flow must have this signature. So you're not allowed to basically create a source from WebSocket because WebSocket is a two-sided connection and it's impossible to be a source. So we can again create some queue, and dynamically whenever we receive some message via WebSocket, we'll just offer that to queue. And basically these messages have some list of advertisements, and we just want to extract those two. So we just want to parallelize our stream. So we'll use map async unordered, and we'll have some simple extract adds method that will just parse some JSON and provide list of adds if they are in a message, if they are not just empty list pass. So since our sync is Kafka, we need to wrap our adds to produce a record. So we have some simple method that will just wrap our add to produce a record. It will just contains topic, parameter, message ID, and message payload. Basically, here will be JSON, but you can use any format you want, like Avro or protocol buffer. And we will basically just map it to produce a record. And this stage is maybe a little fuzzy, but map concat in Akka Stream is basically the same as a flat map in standard Scala collection. So basically, here we will have a list of advertisements, but Kafka sync requires single element. So we just do map concat, which is equivalent to flat map or on standard Scala collections. And you can imagine how this can be complicated if you are not using Akka Streams. Basically, you will need some WebSocket client, you will need the Kafka client, you will need some JSON processing library. But this is, just a few lines of code, and you have production-ready pipeline. And the final example basically will show you how you can batch your streams. I think this is the most the easiest one. So basically, let's say that we constantly receiving some database requests, and we just don't want to overwhelm our database by sending millions of messages per second, but we just want to group the elements and then do some bulk insert in our database. So we have some database actor. It will just store, some string values. We have an option to insert single element, and we have an option to insert the list of elements. We'll just, just set a behavior. It's like we did in every actor before, and we'll just handle insert and insert batch messages. But what is most important is in the next slide. So we have some records, and we want to pass that records to actor. So this pipeline is simple. It will just take every record, wrap it in our insert message, and just send it to actor. But it can overwhelm actor by sending a lot of messages, a lot of single messages. So what we just want to do, we just want to group our elements and make batch of them, and then do some bulk insert to our actor or our database and call some external API. So we just need to use group within simple method, but extremely powerful. It requires two parameters. The first one is our batch size, and another one is timeout. So basically, if our batch is 1000 and our timeout did not expire, it will flash that batch downstream. But if our batch is smaller than 1000, our timeout is expired, it will also just flash downstream this batch. This is really one of my favorites combinators from Akka Stream. And I think this is the final example. So thank you everyone, and thank organizers for accepting my talk, and also credits to SliceGo for this great template. And do you have any questions? I didn't see chat.
Thank you very much, Aleksandar. If anybody has any questions, please post them in the chat. I'll start with...
I just forgot to add GitHub, but it will be later or tomorrow. I will send you email so you can share on a website.
Oh, thank you very much. And when you do send me that, I'll definitely send an email out to all the attendees so that we all have that GitHub link. So I had a question on probably the most interesting aspect of this that I found is how the back pressure itself is handled. So you had one example where you had a publisher. In your WebSocket example, you had a publisher which was publishing messages.
Okay.
So what exactly would happen in this case if your publisher was publishing more quickly than the rest of your system could handle? Would something be blocked somewhere?
No, basically, you can, when you define source, you can, basically, our source is queue now, and this is the buffer side, and this is overflow strategy. So if overflow strategy is back pressure, which is optimal, then message won't be lost, but you have other overflow strategy, for example, to drop new message or to drop old messages in a buffer. But if you can overflow, then it will just slow down the publisher and we'll still have the time to process the messages.
Okay, but if the publisher speed isn't something that you can control, I assumed that in this particular case you couldn't control the publisher speed. Would it just not let, it just wouldn't let another message on the queue? Presumably when you offer the message to the queue, either it would get rejected or it would block at that point, or is that not correct?
Yeah, I'm not sure that I know the answer for this. But basically, you are basically calling with Akka, Akka Http client. You are sending the WebSocket request. So basically, I think maybe internally Akka WebSocket client handle, for us this.
Okay, all right, that would make a lot of sense then. If it was a different kind of publisher, then you could slow down the publisher. Cool. All right, does anybody have any other questions? Please feel free to say them out loud or say them in the chat if you prefer. Cool. Well, I found that to be a really enjoyable talk. Thank you so much, Aleksandar.
Thank you.
Thank you very much.